Okay, calculus class. This is the first video that I'm recording. So right now today is March 10th. The due date's March 20th, as I've told you guys. We've got the countdown going. So when I'm out, I don't know when that will be, but when I'm out, make sure you guys watch these videos. You're going to have to rely on each other mostly. Like I said, I've got you guys signed up for Google Classroom, so you can comment questions to me when I'm out. But it's gonna take a little bit more work while I'm out here. So we're gonna still keep moving. I've got these videos for you, so you can hopefully learn a few things here while I'm gone. I'm gonna try to maybe a couple days, maybe do a Google Hangout or something. I'll try to make myself available. We'll see though. That'll kind of be spur of the moment type thing. I don't know exactly. It's not something I can schedule. So let's go ahead and at least get started here on this section. So 5.4. This is a very important section. That's why I want to get started here videotaping this. Now I might be in class for some of this. I might instruct you guys on some of this to start with. But I'm just going to go through it all, and I'm going to break this down into two videos because there's two parts to the fundamental theorem of calculus. Okay? So here we go. Let's get this thing started. So first of all, let me write down, I want you guys to write down notes just like you normally would. So write this down here. Let's go ahead and get down the fundamental theorem of calculus part 1. Okay, this is the first part. So here we go. Scrolling down. Here's the first part. So, first part of the first part, I guess you could say. So here it is. The fundamental theorem of calculus says if f is continuous on some interval a to b, then this function, and I've got more here, so I'm going to scroll down. Then this function, f of x equals the interval, sorry, I misspoke, the integral from a to x of f of t dt. Now guys, I'll talk about this in a second. I'll go over why we mentioned f of t. This is a different function we're not used to working with. Usually we say f of x, right? So here we go. Let's keep going. Now again, guys, actually not again. I haven't said this yet in this video. Make sure you pause. If I'm going too fast, have the substitute, whether it's Mr. Snyder or Mr. Frazier, make sure they pause here and just let you get this down. Okay? So I'm going to keep going though. It has a derivative at every point in a comma b. So it has a derivative at every point from a to b. And we got some more notation here. So let me scroll down to this entire thing so you can see it. I'm going to draw a picture of it in a second. But write this down. So d of capital F. Now remember what capital F is. What's capital F, McKinley? Means the antiderivative, okay? So d of capital F over x, sorry, over dx, so df over dx is equal to, well, guys, if we take the derivative of the antiderivative, well, here's the antiderivative, we're taking the derivative of that, all right? So that's all this notation is saying, all right? So if we want to take the integral from a to x of f of t dt, that's the antiderivative, otherwise known as the integral. So we're taking the derivative of that, and watch what happens. That's equal to just whatever little f of x is. So I'm gonna tell you what this means in words here, but I've also have it pictorially here, the way you can think of it. So I'm gonna scroll down here again. Pause it if you need to, but I'm gonna keep going to keep these videos shorter. So pictorially, let me talk about this here. So if we have some function, this is just some general function, f of t. All right, that's my function. Now the reason why I labeled it f of t instead of f of x is I want to use x for a different purpose. I'm going to call x some value in between a and b, okay, in between our interval here. So if we do this, what we're saying is that we're trying to figure out, so let's do this first. So let's say we want to figure out the integral from a to x, okay, which is what we have written down right here. This is the integral from a to x of this function, f of t dt. So if we want to figure that out, this would be, sorry, let me undo that. This would be our integral, the area under the curve, right? We've mentioned this before. All right, the integral is the area under the curve. So if we want to figure out the area under the curve, we find the integral from a to x. And so let's say I wanted to find the derivative of that integral. So guys, I could make x as big as I want it to be. I could move x all around here if I want. So I could change x and make it look like this. It could be that area. And I can make it a little bit bigger and make it go all the way out towards b. But let's just leave it right here for right now. So guys, in that instance, since I can move x wherever I want to, the derivative of the integral is going to be dependent on x. So therefore, it's a function with respect to x. So guys, that's why essentially all this is saying is, when we take the derivative of the antiderivative, it undoes the derivative, okay? And we can replace x with t because now our function is with respect to x, right? It depends on x. So that's what we're saying, guys. That's all there is to it. I know it looks kind of confusing here when you write it all down in the math notation, symbolically, but that's all it's saying. If you take essentially the derivative of the antiderivative, those undo each other. So that's, hopefully pictorially that made sense. So if I change x around here, then my integral is going to change depending on what I made x. So that's why it's a function with respect to x now. Okay, so let's write this down in words. So in words, the fundamental theorem of calculus, part 1, tells us 3 things. Here are the first 2. So it's telling us, 1, that every continuous function has an antiderivative. That was the first part of part 1. And part 2, it says the process of integration and antiderivative, my bad, let me say that again. The process of integration and antidifferentiation are inverses of one another. That's wrong. Let me fix this real quick. I'm not going to edit this out. Differentiation. That's my bad. Integration and anti-differentiation are similar. They're almost the same thing. Make that change. Michael Jackson, man in the mirror. Make that change. So the process of integration and differentiation are inverse of one another. So if you take the integral and derivative, they're going to cancel each other out. That's one way we say it. Okay. Oh yeah, the third thing it means is that calculus is awesome. That's right. If you write that down, keep writing that down, and eventually you'll believe it. I keep telling you that, but you guys don't believe me yet, right? It is awesome. All right, so let's keep going. Let's move on to the next. So we're just going to do some examples. All right, just going to look at some examples here where we apply this fundamental theorem part 1. Here we go. So we're going to look at these first 2 examples. These are both pretty simple. So we're just going to use that theorem there. So the 2 examples we have, we want to take the derivative of the integral from negative pi to x of cosine of t dt. Alright, so that's all we want to do. So essentially, guys, all we're trying to do, so for example, this is a function with respect to t right here. So let me kind of break it down for you, how we had it written back here. Alright, this guy. Let's break this down. So I can rewrite this. If I rewrite this here, I can rewrite it like negative pi over, no, sorry, the integral from negative pi to x of just f of t dt, because isn't that a function with respect to t? All right, that's dependent upon t. So guys, right here, this almost exactly applies to the first part of the fundamental theorem of calculus. Fix this. So guys, look at what it says. It says that if we take the derivative of the integral from a to x, and by the way, we do have a constant here. A is always going to be a constant. Our constant was negative pi in that example. Of f of t dt, then the answer is always going to be f of x. So I can rewrite this as f of x. Right? Isn't that the same thing? Isn't that just applying the fundamental theorem of calculus exactly? Okay. So if that's f of x, guys, Well, f of x just means I can take that function. If this was f of t, it's cosine of t dt, then f of x would be cosine of x. That's our answer. So basically we can just replace the t with x, and that's all there is to it. Alright, hopefully that made sense. I don't know if that was the most clear explanation there. We're just going to do this next example. This one should be quick too. Again, we want to take the derivative of an integral. In this case, the integral is from 0 to x. So we got 1 over 1 plus t squared dt. So if we want to take the derivative of the integral, essentially those cancel out, and so what we're going to be left with is basically just that function. And then, well, what else the fundamental theorem of calculus tells us is that we can replace the t with x. So guys, this is all there is to it. 1 over 1 plus x squared. That's the answer. So the derivative and the antiderivative, they cancel each other out. We're left with what's underneath here, or sorry, what's inside here, and we just replace t with x. That's all there is to it. Okay. Carson, wake up. Somebody shake him. The other day he fell asleep with his eyes open, so somebody shake him and make sure he's awake. Alright, here we go. Next thing, we're going to move on. This is another example, but this is a little bit different. Okay, here we go. Find dy over dx if y is going to equal the integral from 1 to x squared of cosine of t dt. Alright, now this one's not as easy as just plugging x into our variable. Alright, I'll just go ahead and warn you here. It's not as easy because of this. The x squared. Alright, so the fundamental theorem of calculus tells us this. Let me write it down again just so I don't have to keep flipping back to it. Alright, so here's what it tells us. It tells us if we take the derivative of the integral from a to x of f of t dt, then that's the same thing as f of x. So again, derivative and integral cancel each other out, so we're left with just f of x. Sorry, we'd be left with f of t, but we can plug x in for t. Right, so that gives us f of x. But the reason we can't use this exactly is because of that guy right there. It's x squared. This just tells us what happens if it's from a to x. So what you do in this case, if you have something other than x right here, you need to think in terms of chain rule, okay? So let's go back to chain rule and think about that. I'm going to review that a little bit. So in chain rule, we did it a couple different ways. I think the way I told you most frequently was, in order to differentiate using chain rule, you take the derivative of the outside function, leaving the inside function alone right away, and then multiplying by the derivative of the inside function. But another way we did it was use substitution. So let me show you that way real quick. So we're going to let u equal x squared. The reason for this is because I want to make this look more like, I want to make this look more like this so I can apply the theorem. Okay, so let's go ahead and get started here. If we let u equal x squared, then what do we have in our function? Well, we're going to have y equals, let me do this in green here. We're going to have y equals the integral, still going to be from, I think it's, from 1. And instead of to x squared, we just let u equal x squared. So it's going to be 1 to u of cosine of t dt. Okay. So now, like I said, we're going to think chain rule here. So if I want to find dy dx, which I think the problem tells me to find dy dx, that's a derivative. So right now, this is our original function, y. We want to find dy dx. So if I want to find the derivative of y with respect to x, that is dy dx, then I'm going to have to differentiate the other side as well. So let's find the derivative here. So it's going to be d over dx of the integral from 1 to u cosine of t dt. Okay. So hopefully you guys are with me here so far. We're not there yet. We're getting close. We're getting there. So let me just write this up here real quick. I'll put recall. Recall the chain rule. This was one way we wrote it. dy over dx is equal to dy over du times du over dx. That's just review from derivatives. Okay? Again, derivative of the outside function, leaving the inside alone right away, and then multiply by the derivative of the inside function. That's what this means. Okay? So in order to differentiate this whole thing right here, what I'm going to need to do is first I'm going to look at the derivative of my entire function. So it's going to be this d over dx of the integral of 1 to u cosine t dt, and then we're going to need to multiply by du over dx. So guys, let me point to what I just did here. This right here is the derivative of the outside function. This right here represents the derivative of the inside function. Okay? So there we go. So guys, now that we have it written like this, look at what we've got. This right here is exactly, except we put u instead of x here, but this is exactly the fundamental theorem of calculus, part 1. This right here, that's the fundamental theorem of calculus. So what we can do is we can just take our function and replace wherever we see a variable with x. Or instead of x, u. Alright, so let's do it. So the derivative of this whole thing right here is just cosine of u. We're done with that. Again, a is just some constant. It's not going to change anything. As long as it's a constant, that's all we need. Alright, let's keep it going. And then we need to multiply it still by du over dx. Okay, we're getting there. Now we're going to start substituting stuff in. So guys, look at what we have. We knew what did we let u equal at the beginning of this thing? Well, we let u equal, let me go back up, x squared. So we need to replace u with x squared. Sorry, my voice cracked a little bit. Nothing new, right? So it's going to be cosine of x squared. And then we need to multiply by the derivative of u with respect to x. So if we go back up here, what is the derivative of u with respect to x? And hopefully you guys said it's 2x. And so our answer, guys, is 2x times the cosine of x squared. That is the final answer. Okay, let me explain this a little bit further before I move on. Alright, so let me recap what we just did there. So what we did, first of all, I saw this was a little bit different than the previous two that we've just done. Okay? This had an x squared in it instead of an x. So if that happens, you need to think chain rule. Okay, and we'll get to that in a second. So think chain rule. The reason why I need to think chain rule is because, well, I need to apply the fundamental theorem of calculus part 1. This right here is it, but notice that has to be an x, not x squared. Okay? So what I did is replace whatever you have in your upper limit of integration, whatever your upper limit is, replace that with a u. Let that be equal to u. Okay? If you do that, then you can apply the fundamental theorem of calculus. But you have to account for your chains that you just made. So, in order to use the chain rule here, we always take the derivative of the outside times the derivative of the inside function. Okay? So, if this is the derivative dy over du, this whole thing would be dy over du. And then we need to multiply by the derivative of the inside. Well, the derivative of u is 2x. Okay? So that would be the derivative there. So that's why, notice kind of what we did here. Essentially, guys, if you notice this shortcut here, all you got to do is take that value, if you get the hang of these, take this value right here and substitute it in for t, okay? And then multiply by the derivative of that value. Okay, that's the shortcut to doing this. So I was trying to explain why this is true. But yeah, if you want to plug that value in for t, and then you always have to multiply by the derivative of whatever that is. Okay, so if that's x squared, the derivative of that's 2x. So that's it. Alright, let's keep it going. A couple more examples. Just looking at the time, we've got about 19 minutes. I'm going to try to make these less than a half hour, these videos. So here we go, let's keep going. got two more examples. So we're going to find dy over dx. So write this one down. Again, pause it if you need time to write it down, but I'm going to go ahead and talk about it. So, we've got y equals the integral from x to 5 of 3t sine t dt. Alright, so 3t times sine t, and then we got this dt. All right, we're always going to have that d something, whatever the integration, whatever variable we're integrating with respect to. Okay, so first of all, what we need to do here is look at it and see, can we just go ahead and apply the fundamental theorem of calculus, part 1. And, well, hopefully you guys notice that we cannot do that. There's something a little bit off about this thing. All right, we're going from x to 5. Well, the fundamental theorem of calculus, I'll just flip back to it on this screen. Here's the fundamental theorem of calculus. Well, we had it backwards, or we have it backwards, don't we? Okay, so since we have it backwards, well, wouldn't it be nice if we could just flip it? Well, there are rules, there are integration rules that we talked about in section 5.3 that we can use here to do that. So I want you guys, if you need to look back at them, go ahead, but hopefully you guys see what we need to do here. If I've got to flip these guys, if I want to change positions there, I want to switch my upper and lower limit of integration, then I'm allowed to do that as long as I make the entire thing, what? That's it, exactly, negative. So it's going to be negative from 5 to x minus the integral from 5 to x of 3t sine t dt. We got y is still equal to that. And so guys, our directions were to find the dy over dx. So I need to differentiate both sides. I need to take the derivative. So it's going to be d over dx of negative the integral from 5 to x, 3t sine t dt. And hopefully you guys have found that this is pretty easy from here. Now that we have this exactly, the fundamental theorem of calculus, we can just plug an x in for t. That's it. The derivative and antiderivative are going to cancel. Now we still have this negative out there, so it's going to be negative 3x sine x. That's the answer. Okay. So that would be the derivative of this integral. Negative 3x sine x. Alright, last one. And I think this one's I think this is the toughest example, so let's get to it real quick. So we've got y equals the integral of 2x to x squared of 1 over 2 plus e to the t dt. Okay, here we go. So, there's a couple things that I have to worry about here. And that's, the two things are this guy and this guy. Those are the two things we need to worry about. The reason we need to worry about those is because it doesn't match up with the fundamental theorem of calculus, which I wrote back here. With the fundamental theorem of calculus, this has to be a constant. This has to be just x, okay, not an x squared or anything like that. So if I want to adjust for that, well, first of all, let's try to adjust for not having a constant down here. I want to try to make this a constant. So this is going to take a little thought, guys. So just give me a second here. Let me go through it. Let me walk you through this. So how about we do this off to the side? Okay, it's on a separate sheet here. Do it on your own sheet. Just put it off to the side here when you're taking notes. So I've got 2x and x squared. Oh, sorry. X sub 2, x squared. Now, guys, I don't know what this function is, what it looks like. I'm not even going to graph it. I don't really have to. I'm just going to draw, in general, just a different graph, okay? This is a completely separate graph. Don't try, like I said, I don't know what that graph looks like. I would graph it normally. I can't think of what that graph looks like off the top of my head. So I'm just going to make up a random function here, okay? So here's my random function, and I'll keep it going. All right. So there's my random function. And this would be my lower limit of integration. This would be my upper limit of integration. So if I want to integrate that, I would be wanting to find the area under the curve again. So, well guys, what I was mentioning, 2x is not a constant. We want to try to get this to look like a constant. Well, I need to just introduce some constant of my own here, and I think the easiest constant to introduce would be 0. Okay, so let me try to explain this, guys. If I wanted to find the area under the curve from 2x to x squared, well, that would be this area right here. One way I could do that would be, and hopefully this makes sense, one way I could do that is to find the area from 0 to x squared, from here to here. So that whole thing. And then subtract it from the area from 0 to x. Let me do this in purple. That area. So if I take the area in red minus the area in purple, wouldn't that have to give me the area in blue? Okay? So that's the idea here, guys. That's what we're going to do. So let me write this out, and then we're going to be able to use the fundamental theorem of calculus. So here we go. I want to try to make this, instead of from 2x to x squared, let's let it go from 0 to x squared. Now that's a constant, isn't it? All right, hopefully that makes sense. So we have a constant. That's going to help us when we apply the fundamental theorem of calculus. So it's still going to be 1 over 2 plus e to the t dt minus, I'm going to subtract here. That's what I talked about, right? We're going to subtract the two areas. The integral from 0 to 2x. Now that's going to be my upper limit from 0 to 2x of 1 over 2 plus e to the t dt. Okay. So both of these are going to require chain rule because, again, neither one of these is x. Okay, so we're still going to have to use the chain rule. But I still want to take the derivative of this. We want to find dy dx. Okay, this was part B of these directions. So let's do that. So dy dx is going to be the derivative of those guys. Okay, I'm not going to write down d over dx. It's just going to be the derivative here. So in order to figure out the derivative, well, I still need to plug in x squared in for my variable. I'm going to use the shortcut that I talked about earlier. And then I need to multiply that by the derivative of our u. We let u equal x squared. Okay? And so now the derivative of u has to be, just like in the last problem, 2x. So that is the derivative of the integral here. Same thing over here. So we're going to subtract. We still want to plug in. Now, we don't want to plug in x squared anymore. We're going to plug in 2x. E to the 2x. And then we need to multiply by the derivative of 2x. So what's the derivative of 2x, guys? Or Ashley, you tell me what it is. Yep, that's right. 2. I'm hoping you said 2. I'm counting on you, right? Alright, so here we go. So I'm just going to clean this up a little bit. That's all you can do. We're pretty much done. We just got to clean up that answer. I'm going to put the 2x on top here because that's 2x over 1. And I'm going to put the 2 on top here. Okay, so dy over dx. Got it. Okay, that's it for this video. Thanks, guys.